In this video, I'm gonna be explaining a very important article, Overcoming Catastrophic Forgetting in Neural Networks. This important paper in 2017 by DeepMind. The ability to learn tasks in a sequential fashion is crucial to the development of artificial intelligence. Neural networks are not in general capable of this, and it has been widely thought that catastrophic forgetting is an inevitable feature of connectionist models. We show that it is possible to overcome this limitation and train networks that can maintain expertise on tasks which they have not experienced for a long time. Their approach in their article remembers all tasks by selectively slowing down learning and the weight's importance for those tasks. This phenomenon is called catastrophic forgetting and occurs specifically when the network is trained sequentially on multiple tasks, because the weights in the networks that are important for task A are changed to meet the objective of task B. And from B we go to C, and C to go to D. So the probability of catastrophic forgetting may increase or may decrease sometimes. Whilst recent advances in machine learning and in particular deep neural networks have resulted in impressive gains in performance across a variety of domains, little progress has been made in achieving continual learning. Current approaches have typically ensured that data from all tasks are simultaneously available during training. By interleaving data from multiple tasks during, for example, if I say data A, some of data B, then again some of data A, some of data B. This is called interleaving. By interleaving data from multiple tasks during learning, forgetting doesn't occur because the weights of the network can be jointly optimized for performance on all tasks. In this regime, often referred to as multitask learning paradigm, deep learning techniques have been used to train single agents that can successfully play multiple Atari games. If tasks are presented sequentially, multitask learning can only be used if the data are recorded by an episodic memory system and replayed to the network during training. This approach, often called system-level consolidation, is impractical for learning large numbers of tasks, as in our setting, it would require the amount of memories being stored and replayed to be proportional to the number of tasks. What is the motivation for this elastic weight consolidation? In brains, synaptic consolidation enables continual learning by reducing the plasticity of synapses that are vital to previously learned tasks. So there is a trade-off between stability and plasticity. So the more stable, it means you're fixing the weights. But plasticity, you put some room for changing some of the weights. It's not fixed. It can vary. And so we implement an algorithm that performs a similar operation in artificial neural network by constraining important parameters to stay close to their old values. In this section, we explain why we expect to find a solution to a new task in the neighborhood of an older one. How we implement the constraint, and finally how we determine which parameters are important. For example, this is the area for task A that the loss is less than a threshold. And you see the intersection is very important. because they agree for both tasks. And if you just write the Bayes rule, parameter probability of parameters given your data, you know these are in the numerator, and this is in the denominator, it becomes a minus because we are checking the log. And now our data is composed of two tasks, for data for task A, data for task B. And we can write it like this. But I will work on this formula in the next lecture. So next lecture is very important if you want to understand what you do after deriving 2, what do you want to do. But for now, you should know that in this paper, they just minimize the loss of task B, but they don't let the weights to be very, very far away. They don't let it to be very far away from the weights of the previous task. And I will explain this matrix, this Fisher information matrix, which is very important, in the next lecture. How you derive it. Just write a Taylor series and you will see it's so simple. And so this is just a quick review of Fisher information matrix, which is this expectation given your parameters. So for any I and j, if you have many parameters, for example, I could be 2, I could be n, for any of them, so this is for example, I and j's entry, the i's row and the j's column, you can derive the entry will be this expectation. So we are varying it with respect to the row, and we are varying with respect to the j at that specific row and row and column, given your parameters. If you do that, this is the Fisher information matrix, which has which has a lot of information. But I will explain it in the next lecture.